My dear people, hope you're all doing well. This is Dr. Venkat, and welcome to this week's lecture on hydrostatics and buoyancy. Well, this week I'd like to discuss with you all about the force and the pressure that is exerted by fluids that are not moving, and we'll be looking at why some of the objects float and why some of the objects sink when they are immersed in water. This is going to be very interesting. Let's get started, shall we? This week, just to give you all a glimpse of what we are going to be looking at, we'll look at what is hydrostatic pressure, hydrostatic force. We'll be looking at some of the pressure measurement instruments. I'll just introduce them to you. We'll be looking at the buoyancy principle that was stated so many years ago by Archimedes. We'll be looking at the effect of volume on buoyancy. How a material, when it changes its volume, how does the buoyancy of that material changes? And we'll be looking at some mathematical problem. In the last 2 weeks, as you might remember, we have been looking at the flow of fluids. Otherwise, whenever fluids are moving, so we looked at continuity equation and we looked at Bernoulli's equation. One of the important applications that I really wanted to discuss with you guys, and perhaps I'm not sure if I discussed it or not, is this. Whenever you're trying to ventilate your room early in the morning or late in the evening, etc., so I have seen quite a number of people just opening the window alone or just one door for the room to get ventilated. But if you think of continuity equation, Bernoulli's equation, or anything in mass flow rate, if you have an inlet, there should be an outlet for fluid flow to happen unhinged. So only one if there is only one entry, then air will enter the room. It will just try to circulate around, it will create a static pressure, and then it will have to go out through the same way. It is quite difficult, and so the ventilation does not happen properly. So for the ventilation to happen properly, especially during the COVID times, yeah, you should open both the door and the window, or any window on the opposite side of the room, so that air has an entry and an exit. Yeah, so of course, my dear people, I really care about your health, and so does the university. So it's quite important for you to relate something as important as ventilation, ventilating your room, keeping the air in the room fresh with that of whatever we have been learning. Is that okay? Now, this is what we have been looking in the last 2 weeks, but this week we are going to be looking at fluids that are not moving. That is why it is called as hydrostatics. Hydro is water, statics is not moving or stationary. So, that is what we are going to be looking today. Well, what does pressure have to do with climbers when you're going inside a tunnel in a train, or when you are traveling in a flight, when you're going on a balloon? This photograph is from the Bristol Balloon Festival. A diver, someone who's trying to climb a mountain, and a water tank at a height. What do they all have in common? What is it? What? Exactly, my dear people, exactly, pressure. Yeah, pressure is the common thing. That is what we'll be looking at. So whatever we are learning today is applicable everywhere. So when you're going inside a tunnel in a train, what happens? Your ears pop. Sometimes when you're going in the flight, your ears pop. What is the reason? Pressure. Yeah, similarly, when someone is diving in water, when someone goes diving, what happens? The pressure that they experience is very high. Yeah, and when someone is climbing on a mountain, the pressure that they experience is very low, so they have to have all the proper equipment so that they'll be able to live and to survive, either climbing the mountain or going under water for exploration. Yeah. And also, whatever we are going to be learning is so very applicable for anything, including the glass of water that we have, wine that we have, any water tank whatsoever. Yeah, it's applicable everywhere, my dear people, and that is what we are going to be looking at for today. Well, let me ask you all a question. You know what, this is something that you can do in your own home. So take a water bottle or just a glass or any container, just hold it. So it's going to have a certain weight, otherwise it's going to be exerting certain pressure on your hand. Now what we can do is that we can fill it with water or any other liquid. Let's say water is quite easy, you know. So let us fill that container or the glass or water bottle with water. Now what happens to the hand? Is it going to experience the same force or is it going to experience a different force, my dear people? Your hand, tell me. What what is it? Exactly, it's going to be heavier, otherwise the water can with water is going to exert more force on your hand. But if you think of it, what is creating this increased pressure or the increased force? Hmm? What is it? Exactly, it's the water that we have added. Yeah. So, is it important for us to calculate, yeah, and to measure and to know what is the pressure that the water is exerting on our hand? Is it important? The force that's exerted on our hand. It just feels like a common thing, carrying a water bottle or carrying a glass of water in our hands. But is it important? Of course, my dear people, of course, it's very important. Yeah. If we do not, if we are unable to calculate this, if we are unable to measure these values, then how are we going to construct water reservoirs? So the water reservoirs that are being constructed, the what is it called as, you know, in the canals they have this locks. Exactly, construction of locks, making any water tank that they have in house, water tank that the city council has. You see, all of them are made calculated and created with whatever we are going to be looking at. Yeah, that is the reason it becomes so very important for us to measure the force and the pressure that is exerted because of the liquid. So as they say, hydrostatic pressure is nothing but the pressure that is exerted due to a static liquid. This is quite important, static liquid, otherwise the liquid is not moving. Look at this glass of water here. Yeah. So what does it say? It says that the pressure, well, the pressure that is exerted, yeah, by the water at the bottom of the glass is the hydrostatic pressure. Now you might be asking, what about on the sides, Venkat? Is the water exerting force on the side? Of course, my dear people, of course it's exerting some force, some pressure on the sides. Yeah. And it says that it acts in all directions equally. Yeah, what it means is that if I'm going to be looking at the top view of this circle, of this of the, what is it, of the rim. Yeah. So the pressure at one point, let us just take this point, this level, it's going to be same in all directions, otherwise the magnitude is going to be same in the same level. Yeah. And it says that it acts at right angles to all the surfaces. My dear people, this is quite interesting. Yeah, look at this. So when we have this glass of water here, yeah, the right angle to this particular surface here is over here. Yeah, so it acts over here. And what about the right angle to this one? It's over here. Yeah, so it acts at the right angles to all the surface. But what about a wine glass then? Let us look at this wine glass which is filled over here. And then what about the pressure that is acting? Of course, my dear people, it's going to be acting always at right angles, always. Yeah, right angles to the surface. Yeah, it's always going to be acting at right angles. Is that okay? Yeah. This is what hydrostatic pressure is all about. So this is a very common experiment that everyone, well, most of the people would have done in your school, in your GCSE, A levels, even in your class 5, 6, 7, something like that. Yeah, in which you have like a tank, and there are three holes that are made in the tank. One, two, three holes that are made in the tank, and then water just jets out, yeah, of these three holes. So now, which hole will have the strongest jet? Well, here it says, of course, yeah, the lowest one will come with a very strong jet. This is with a medium or moderate jet, and this one will come with a slow jet or the weakest jet. So what is the reason? What is the reason that on the top it is coming with the weakest jet and the bottom is coming with the strongest jet? What is the reason, my dear people? The reason is there is a lot of water pushing at this particular layer of water. Yeah, there is a lot of water that is pushing. So that is what is creating, otherwise there's a lot of pressure on this particular layer of water, so that it comes out as the strongest jet. Whereas here, if you look at it, the amount of water that is exerting pressure on this layer is comparatively less. Do you see? Yeah, that is the reason why it happens. So can we say that pressure increases with the depth from the top, yeah, the height from the top. So here the pressure P1, yeah, and the pressure P2, we can say P2 is greater than P1. The only difference is the height. The density of the liquid doesn't change, the gravity doesn't change, the only thing is the height. So as height, otherwise as depth increases, let's say that way, yeah, as depth increases, pressure increases. As the depth decreases, the pressure also decreases. Yeah, so otherwise pressure is directly proportional to the height from the top or the depth. Yeah. This is the reason why divers who go deeper and deeper experience more pressure, because there is more water on the top of them exerting pressure. Yeah, and the pressure equation, my dear people, is pressure equals rho g h, where rho is the density of the liquid, g is the gravity, and h is the height from the surface, yeah, or the depth or the height from the surface of the water surface. Yeah, height from the surface of the water. Now let us assume instead of water, yeah, instead of water, in the same water bottle that you took, you take crude oil, yeah, which is really very dense. So do you think it's going to weigh the same thing as water? Of course not, my dear people. It's going to be heavier. Otherwise, and also the pressure the crude oil exerts at the bottom, yeah, is going to be lot more. Yeah, that's why we have written density and the gravity. For example, if I conduct this same experiment with a beaker and three holes in Jupiter, where the gravitational potential is 23 times higher, what happens to this strongest jet? It would come out 23 times longer. Yeah, do you see? Yeah, so gravity. So the formula, the most important formula in hydrostatics that you have to remember is this: P equals rho g h. Pressure due to liquid equals the density times gravity times the depth or the height from the top. Yeah. So since we said, yeah, it's the height from the top that matters, let me show you something very cool and something very interesting. I have a glass jar, yeah, which is quite tall, and the diameter is very small. Diameter is very small compared to this diameter. This is a larger diameter, yeah. And then there is a beaker of a different shape, and then there is a funnel of different shape, yeah. So if I calculate the pressure at each of these points, everyone would usually assume that the pressure would be different. Yeah, that is what my friend told me today as well. When I asked her, oh, can you please tell me what do you think the pressures are going to be, she was like, oh, of course it's going to be different, the shapes are all different. But then when I explained, its pressure is nothing but rho g h. There is nothing here which talks about the shape of the, what I said, the shape of the beaker. It doesn't talk about the area or anything. It's all about the height. So at this height, the height is h. Here the height is h. Here the height is h. Here the height is h. So the pressure is the same in all these beakers. One, two, three, four, all these beakers will experience the same pressure at the bottom. That is so cool, is it not? So cool. But my dear people, there is one more thing. Okay, the reason why my friend got confused, and also some of you might be confused, is you might be thinking of the force. Yeah, if you think of the force, what is force? Force is pressure times area. So the total force experienced, yeah, at this and number 4 would be different to the force that is experienced here, would be different to the force that's experienced in all these things. Yeah, the force would be different dependent on this area. Area 4, area 3, area 2, area 1. Yeah, the force might be different, but the pressure is always the same. Is that okay, my dear people? Yeah, I want to discuss with you something even more interesting in the next slide. Unclogging a sink. You know what, I have done this when I was little as well. Well, this common mistake of how to unclog a sink. So whenever the sink is clogged, what some of my friends and even you might be doing this now, yeah, what they do is they just plug this, and then they open the tap completely and fill the sink. If this is the sink, yeah, this is where it is, and the clog is here, let us say. Yeah, so what they usually do is they just plug it and then they just fill it with water. And what they think is, and even some of you might be thinking, that all this water, all this water over here will be applying pressure on the clog. What do you think? Do you think it's true? Not at all. That is a complete misconception, my dear people, because the layer of water here will be exerting a pressure over here. Do you see? Yeah. So all this water is not really useful at all for unclogging the drain. So what can we do to save water and to unclog it properly? So let me show you an example. Let me show you how to do it. Yeah. So if the clog is here, what we can do is we can put a long PVC pipe, or not even a long one. We do not just like 30 centimeter, 40 centimeter pipe just on the top of this, and then fill this with water. So what will happen, the pressure experienced by the clog would be very high compared to all this water over here, because the water is only H, which could be usually 20 centimeter, whereas this one is going to be 30 to 40 centimeter. Woohoo! So much pressure experienced by the clog, and it would just go away. Yeah, and also it saves a lot of water. Do you see? Do you see how to unclog a sink? Huh? Fantastic, fantastic. Okay. Now this is quite an interesting thing, my dear people, about pressure diagram or the pressure prism. Yeah. Now, I told you that the pressure experienced by the bodies depend on the height. Yes. So let us take this particular what is it, square body, a cube that is immersed in water. This is supposed to be the surface of water. Okay. Let us just draw a small fish somewhere here. I know it does not look like a fish. Okay. Yeah. Okay. There is a fish. Okay, let us draw one more fish so that we do not want it to be all alone. There you go. There are two fishes, they are friends. Their names can be James and Dominic. Yeah. I have no idea why. Okay, now, my dear people, this particular cube is sunk in water. So, what is let me just draw the pressure that is experiencing. Now, if you think of it, this is at a height H. Yeah, otherwise this is going to experience a pressure of rho gh. Let us say this is 1 meter. Yeah, so this is going to experience a pressure of 1 meter, equivalent to 1 meter, and it's all going to be at right angles. So can I just draw like this? Yeah. Okay, this is the pressure that's experienced over here, and they are all at right angles. Now let us draw. What about the pressure here? The pressure would be the same as this. At this, the depth is increasing, is it not? Compared to this point here, the depth is increasing, so I have to draw longer lines. Longer line, longer line, longer. Ooh, there you go. And you draw. Usually it's like this. Yeah. Then what about at the bottom? This is going to be the longest one. Otherwise, at the bottom, it's experiencing very, very high pressure. Do you see? Yeah. Let me just rub it off. Wait. Yeah. Otherwise, if I draw it, it's going to be like this. This is very long. Yeah. And on the side, it's going to be like this. Do you see? And also on the other side over here as well. But what about if if a sphere or ball is immersed in water? What is the pressure that it is going to experience? Let me draw that for you. Okay, it's always at right angles, don't forget that. If I draw it correctly, it's going to be like this. Yeah, this is going to be the pressure prism. This is what we call as the pressure prism. Yeah, so for example, let us look at this particular tank in which water is inside. So how will the pressure be acting here? The pressure is zero, the water pressure is zero, because rho gh, is it not? The pressure equals 0 pascals. The reason is it is rho g h is 0, and the maximum would be here. This is P max. So if I draw, it would be 0. It's going to be like this. This is the pressure prism for this side. What about for this side? It's going to be again like this. Do you see? Yeah. Have a look at some more examples. If the body is exactly at the surface of the water, how is the pressure prism going to be? Let me draw it for you. It's going to be like this. Yeah. This takes into consideration only the water pressure, not the atmospheric pressure. My dear people, you might want some problems to be solved. I have solved some problems for you guys. The PowerPoint is on Blackboard for you all. All that you have to do is you can also click here to watch the video. The link is given in the PowerPoint. I'll also put the video link in the description box or something like that, as they call in the YouTube. Yeah, I'll put those two videos below. There are two problems I've solved for you. Have a look at them and we'll discuss them during the tutorial. Is that okay? Yeah. In the next section we are going to be looking at why some of the objects float in water and why some of the objects sink. Bravo.